Entonces es un placer presentar a Jonas Deré de la Universidad de Leuven Kulak,
Leuven Kulak.
Él nos hablará sobre the structure of underlying Lie algebras.
Thank you. So yeah, I didn't understand everything in Spanish, but so the L here is for Leuven and the K is for Kortrijk. So Kortrijk is a very small city, like 100 kilometers of Leuven. So the main campus is in Leuven and Kortrijk is a separate part where we are at. Okay, so I will talk about the structure of underlying Lie algebras, and maybe you've seen in the abstract that it will be a bit more algebraic maybe than you're used to, but I'll try to keep it as geometric as possible. And actually the problem that I studied comes from a geometric problem. That's where the origin is from. And I'll start by giving a bit of background for that. So the geometric motivation for the question was the following. So suppose you have an almost Hermitian manifold. So you have a manifold M, you have some Riemannian metric G, and an almost complex structure where these work together well. So this is like an isometry for the metric. Well, on these manifolds, you have a very nice connection, a unique connection, not the regular Levi-Civita connection, but one that's much more compatible with this structure. So what is the properties you have for this connection is that on the one hand, it behaves well with the metric. On the other hand, it behaves well with the almost complex structure. And the third property you have is that if you look at the torsion, well, it will not vanish, but it will have like the 1-1 part with respect to this almost complex structure will vanish. Okay, so those are the three properties and a connection satisfying these three properties. So this unique connection is called the Chern connection. Okay. And given your manifold M and this connection, you could study all sorts of properties. And the one that was studied, that people were interested in, for example, was, well, if you assume that so there are two properties. The first one is that the manifold is what we call Chern flat. It just means that the holonomy group of this connection is trivial. And the second property is that it's quasi-scalar. So that means, let me write this, quasi. That's if, so you take the two form with this structure and you don't take the full D but only this part is 0, then you call the manifold quasi-scalar. And so people were interested in manifolds which are both Chern flat and quasi-scalar and compact. So the question was, if M is compact, Chern flat and quasi-scalar, what can you say about M? And maybe before I continue, I will give an example of a manifold which has this property, and then you already see where the algebra comes in. So the example that I will give, you start from the complex Heisenberg group. So if I write H3 of a ring R, that's just upper triangular matrices with one on the diagonal, and where X, Y, and Z lie in this ring R. Okay, I will do this for more than just fields, but also for rings. And in this complex Lie group, you have a lattice. For example, this lattice, we'll call it, so this we call G, this one we call gamma, And the quotient manifold, it's a 6-dimensional nil manifold. That's the easiest example you can get of a manifold with these properties. So it's called Iwasawa manifold, sorry. And before I can say anything about these properties, of course, what I first need is an almost complex structure. And okay, the almost complex structure will not be the complex one. It will be slightly different. So in order to write it, I will take a basis for this. So I'll go to the Lie algebra and write it there. So on the Lie algebra G, I have a basis, x1, x2, x3. So this is the basis as a complex Lie algebra, and I will just take the corresponding I times those vectors. So I have I times x1, that's x4, I times x2, that's x5, and I times x3, that's x6. Yeah, I will. Sorry. And so with this basis, I will write the almost complex structure. So J, okay, maybe first, from this basis you can compute the Lie bracket, and so it's given by x1 and x2 gives you x3. That's just the Heisenberg one. And then you have, if you take x4 and x5, so you have I times x1 here, I times x2, you get minus x3. And then you can do x1 and let's say x5. This will give you x6, and x2 and x4 will also give you x6. So that's the relations you have in this Lie algebra, all of them. And okay, the almost complex structure J is a map from G to G. And it will look a lot like multiplication by I, but it will not be exactly the same. So what we will have is that J of x1 as x4, J of x2 as x5, so that's still multiplying by I. Of course, if this one is mapped to x4, then x4 is mapped to minus x1, so I won't write that. And then instead of mapping x3 to just x6, you will map it to minus x6. So there's an extra minus sign here. That's important. And that's the almost complex structure. And you can compute everything on it, and you will see that it is really so on the manifold you will see that this is of course compact, and it's Chern flat and quasi-Kähler. Well, you still need a metric, but you just, for example, take this as an orthonormal basis, or any other metric compatible with J will do the trick. Okay, so that's the basic example. And so what you see is that this J map, it's not bi-invariant because I have some minus here, but we call this anti-bi-invariant. So J is called anti-bi-invariant. Now what does it mean? It means that if you apply J to the Lie bracket of x and y, you will get minus the Lie bracket of jxy. So that's the same bracket, the same minus here that appears there. Okay. So probably you're more familiar with really bi-invariant complex structures, and that is that's really if the minus is not here. So x j times xy is jxy. Okay. And so this is the first example we have. And actually what was shown in 2012 is that all examples are of this form. So this is a theorem by Di Scala and Vezzoni in 2012. They say, suppose you have some manifold M with an almost complex structure J, then there will exist on this manifold a metric which is, so this one has a metric such that it is quasi-Kähler and Chern flat. This condition is equivalent to the fact that this M is a nil manifold of nilpotency class 2. So exactly as we had before, with this structure that I described here, with J anti-biinvariant. So this is not just an example, it's really the prototype example, and all examples look like this. And I didn't say anything about the metric, but what you can show is that... I'm sorry? Yeah, M is compact. Sorry, I should have. So that was what I said in the question. So we were only considering compact spaces. And so the metrics you have that do the trick are exactly the left invariant ones. The metrics here. So you only have to consider left invariant metrics on these manifolds. Okay, so that's a very strong result, saying that we somehow are able to describe all these manifolds. At least if we are able to describe these manifolds, nil manifolds of nilpotency class 2, okay, that's something we might be good familiar with, but these anti-biinvariant structures, that's the ones we have to study on our Lie algebras. Okay. And then, I think it was more or less in the same year, I didn't write it down, but Jorge maybe knows because he wrote the paper. So, after this paper, Jorge joined the effort and he was able to show, well, they were able to show with the three of them, that these the anti-biinvariant structures, they are really what you expect them to be. They are really biinvariants where you add some minus inside. And I won't explain how to do it. So, but up to the minus, and there's a very good way of introducing the minus, the anti-biinvariant structures are exactly the biinvariant structures. At least up on these two-step nilpotent. So from now on, I will always work on nil manifolds of nilpotency class 2. Okay, and so the true question to classify these manifolds is, can we somehow describe all biinvariant structures? And well, what you might want to do is describe all these nil manifolds, and so the question you still have is which G can occur. So which Lie algebras can you have? So which G have a biinvariant structure? And you know that all of these G, I mean if you have G with a biinvariant almost complex structure, then that's more or less, I mean that's the same as a complex Lie algebra. So So G with the J is nothing more than n, a complex Lie algebra.
So you put a minus in the center, that's what you do?
Yeah, well, no, I think it boils down to the same, but in the paper you do it not in the center, but somewhere else. Like on the... But I don't know why you didn't do it on the center. Maybe something goes wrong in the center.
I don't know.
I also would think that doing it on the center would work, but you do it really on some part in the orthogonal complement of the center. Like there you introduce a minus.
It's the same.
Okay, it's the same.
Yeah.
Okay, so you just do the minus on the center. Okay, and okay, we know classifying all complex Lie algebras, that's not something we want to. Complex two-step nilpotent, of course. That's a hard problem. But maybe this problem of describing the G could be a lot easier than describing all the N, because somehow we forget part of the structure here. And so the question that remained open is, like, given your G, how many of these N can you get? Maybe describing all complex Lie algebras is very hard, but maybe in the end you only end up with a lot less of these real ones. And so the question that remained is, like, if we know the G, do we also know the N? Or how many bi-invariant complex structures can we put on one G? So okay. And that's the question I will answer, but before I do it, I want to make it a bit more general, because, I mean, the original question was formulated only for two-step nilpotent Lie algebras, and also only for the reals and the complex numbers, and maybe that's all that you think that is important, but in some cases it could be useful to study other fields as well. So the more general question, it goes in two ways. One, other Lie algebras, meaning not just two-step nilpotent. And also other fields. So now you have the reals and the complex numbers. So you go from a complex Lie algebra and you forget that it was a complex when you go to the real. You could also do it for other fields. So suppose that N is a Lie algebra over E. And all my fields are of characteristic 0, don't worry too much about it. If you don't want to think about it, just think about the first case. That's good for me as well. You have what we call, NF. It's in the same procedure as forgetting the J here. It's forgetting that it's a Lie algebra over E. You just consider it as a Lie algebra over F. And we call this the underlying Lie algebra. Okay. Now, you would think, why would you want to generalize it in this way? Especially with the fields, maybe you are very skeptic about why I would do that. But there are good reasons, and I will very shortly explain why you would want to consider other fields. Well, maybe first, why other Lie algebras? Well, that's a very easy one. Maybe I should go back to when I started working on this problem. So when I was here 2 years ago, Jorge gave me his paper with this question in, and he said, maybe you want to think about it. And I did. I thought about it while I was here. And after 1 week, I thought, well, this is a very hard problem. I will not get into it because I computed a lot and a lot of examples, and all of them seem to just suggest that the G completely determines the N. And it feels that this should not be the case, but somehow all the examples we have, it is the case. And then I didn't think about this problem for more than a year. And then in Kortrijk, one of the PhD students came to me with a certain Lie algebra, and he was studying, and that's maybe something you already heard of, almost inner derivations. Well, it's not that important what it is. Maybe you heard of it, maybe not. And so this is related to constructing no manifolds which are isospectral but not isometric. So isospectral, they sound the same but they are not isometric. This is by work of Gordon and Wilson, a very nice paper, where they show that if you have almost inner derivations which are not inner, then you somehow get a whole family of these manifolds. And this is not just for two-step nilpotent, this is for general nilpotent Lie algebras. And also this is used, these almost inner derivations, in other fields for other Lie algebras which are not even nilpotent. And so what this PhD student did, he was able to use these underlying Lie algebras to construct almost inner derivations. And I won't explain how it works, but that's how I started thinking about this question again, because he was studying another problem, and this problem was not just for two-step nilpotent. That's the point I want to make. And then a second motivation why you would take other fields than just R and C. Well, this is a bit longer. But in my PhD thesis, I worked a lot on Anosov Lie algebras. And Anosov Lie algebras are rational Lie algebras. And one way of constructing it is by taking underlying Lie algebras. For example, if you take the Heisenberg over Q with the square roots added. So Heisenberg over Q is not Anosov. But if you take this one and you take the underlying over Q, this is Anosov. And this was the first example given of a non-abelian Anosov Lie algebra by Smale in the 60s. So somehow this construction... Borel? Okay. Sorry.
Borel gave the example to Smale.
Okay, thank you for clarifying that. So due to Borel, this is the first, well, it was written slightly different. But you see that this type of field is not Q, it's not R, it's not C, it's something completely else. And that's why, if I wanted to do it, I wanted to do it for other fields as well. And all of the fields I'm interested in will be Q and an extension field. But okay, if you think I don't care about that, just think about R and C. I'm perfectly happy with that, but there was a reason to do it for other fields as well. Okay, now back to the question. Can we find Lie algebras? So the question was, suppose that NF is isomorphic to MF. So you have two Lie algebras, N and M, over the field E. Does it imply that N and M are isomorphic? So this is over E, and this is over F. Okay. And in order, I mean, if you look at this question, there's no good reason to ever believe that this would be true, because somehow you forget structure by going here. You would not expect to recover the structure completely. And so one way of constructing counterexamples is thinking of, so you want to have isomorphisms over F, which are not isomorphisms over E. So you want to look at linear maps over F, which are not linear over E. And so maybe if we just take the easiest vector space, just E itself, I mean, you want to look at maps which are isomorphisms are like linear over F, but not over E, well, we will take an element of this form. So what is it? It's just an automorphism of the field which fixes F. So S sigma restricted to F is the identity.
So from Q to R, the answer is yes.
From
Q to R.
From Q to R.
The answer is yes.
Of this?
Yeah.
I
think so.
That would surprise me. No, I don't think so.
We don't know.
No, it's not true. No, it's not. No, I'm okay.
For the important, I think maybe this.
Okay.
Okay.
I don't. Okay, I can think about it.
We need time extension, right?
Yeah, I should have said that. Yeah, so F over E is finite. Otherwise, this Lie algebra is no longer finite dimensional. So that's the restriction you want. And later on, I will want it to be a Galois extension. But okay, I will write it one that is needed. But in principle, what I'm doing now, it could be. Yeah, no, okay, you need finite in any case for the finite dimension. Okay, but so this is the idea. You have a field automorphism with this, I mean, it's linear over F, but it's not linear over E. And now we want to do this on the Lie algebra. And so that's the main definition. We have a map phi going from, well, I will keep the notation there, N to M. So N and M are Lie algebras. And we call it sigma linear. If, so it's, I mean, phi of x plus y is phi of x plus phi of y. So nothing changes to the additivity, but it has this sigma appearing for multiplication. So what you do is you mimic this behavior, but then on maps between Lie algebras. So if you're just interested in R and C, this is complex conjugation, think about it. And so what you want is that multiplication with I is not just I times that thing, but minus I times that thing. Okay, and we call it a sigma linear, that's map, but we will take it a morphism. We also want the Lie bracket to be preserved. So if you take phi of x, y, that's the bracket of phi of x and phi of y. So it behaves entirely like a Lie algebra morphism, except that it's not linear, it's sigma linear. Okay. And then you can also talk about sigma isomorphisms. That's if phi is bijective. And in this case, if there's a sigma isomorphism from N to M, we will write this, N sigma is equal to N. So somehow N is a conjugate of M in some way. So that's my definition. Now, in order to write this, I didn't really say it. I will say it now. So N sigma always exists and is unique.
But the inverse is not always sigma linear.
No, the inverse is sigma minus 1 linear.
And you are not asking that inverse be sigma linear to be a sigma isomorphism.
No. Sigma isomorphism is really sigma. So in the other direction, it will be a sigma minus 1 isomorphism.
So it's not an equivalent relation.
No, not at all. But what you have is that if this holds, then M is equal to N sigma minus 1. I mean, it behaves well, but maybe not entirely as you want. Okay, so don't worry too much about it. So you always have, like, for every sigma you have a conjugate Lie algebra and it's unique. So this notation is okay. Maybe it was not clear from the definition immediately, but this is a good notation. And so what the main thing is that the sigma linear map, if you consider it over F, it is still linear. So if phi is sigma linear, then if you restrict it to the field F, it is linear. Right? Because the sigma doesn't have an effect here on the lambda. And so what this shows is that although it is not an isomorphism over E, it will induce an isomorphism over F. And so it's very easy to see that the underlying Lie algebra of the conjugate, I will keep on using M, is the same as the underlying of N. So it gives you a way of producing Lie algebras which have the same underlying Lie algebra by taking conjugates. So basically what we now have to do in order to produce a counterexample here is we have to look for N with N sigma not isomorphic to N. Right? That's the question we have to answer. Can we find the Lie algebra such that its conjugate is not isomorphic to itself? And okay, once you realize this, it's not so hard to produce a counterexample. And I will write it down. Okay, I will copy it because it's not so short. Okay, so the example is the following. It depends on a parameter lambda, g lambda, and the basis is 10-dimensional. So you have a basis x1 till x8, and then z1, z2. And the Lie brackets, it's a long list, but it's not that hard what is going on. So x1, x5, x2, x6, x3, x7, and x4, x8 give you z1. And then we have a similar list for z2, but just shifted one, I think. Yeah. x2, x5 is equal to x3, x7, x6 is equal to x4, x7, and then is equal to minus x1, x8, and this is z2. Okay, and now we just have to still have the lambda, and that's the bracket between x2 and x7 will give you lambda times z2 minus lambda times z2. Okay, it's a long Lie algebra, but what is important is that you can show that g lambda is isomorphic to g mu if and only if lambda and mu are the same. Okay. If you don't know how to do this, I mean, there are techniques. This is a nice type of Lie algebra in the sense that its center is two-dimensional, and there's a technique called pencils, and you can study the pencils. And I mean, you could show this. I don't say it's easy, but it can be done. And what you can also show is if you take the conjugate, so in this take complex conjugate of g lambda, that's nothing else than taking the complex conjugate of lambda. And so once we have this, we're there. We just take any lambda which is not a real number, and you're done. You have a whole family of examples where, so this doesn't, so they're not isomorphic, the conjugates, but the underlying are the same. Okay. So in general, we cannot conclude that the Lie algebras are isomorphic. Like the the ones over the field E. But in some specific cases, we can conclude something. Okay.
Are these the algebras of lambda complex? They don't have real form?
Yes. Yes, and I will come to that. So, okay, maybe I should have said that. So, how do you compute the complex conjugate of a Lie algebra? Well, once you have a basis with structure constants, the complex conjugate is just taking complex conjugates of the structure constants. That's all what's going on. And so, in this case, you see immediately that the complex conjugate gives you this one. But it also shows you that if the Lie algebra is defined over the reals, then the conjugate is always isomorphic to itself. And so any example of this type must have that it doesn't have a real form. Okay. So now we will take E Galois over F. Again, if you don't care about general fields, C is Galois over R, there's not a problem. And so what we want to do is suppose that, so you have this underlying Lie algebra. I used N, I will keep on using N. And you have the original Lie algebra, N. And so this is a Lie algebra over F. This is 1 over E, so it's hard to compare them. And moreover, the dimension of these two Lie algebras are completely different because this one has dimension. So the dimension over F is equal to the dimension of N over E times this order of the extension field.
So Galois is just that this is a finite extension plus something?
Yeah, it means. Okay. Galois, well, one way of saying it is that, so I wrote this as this group. So this is a group. The order is always bounded by the extension degree, and Galois means that it's really equal. So it's somehow this group is as big as it can be. Or said differently, it is the splitting field of a polynomial over F. Or said differently, if every element in here, if an element is fixed by every element in here, it must lie in F. I mean, there are several equivalent definitions. But it's somehow the nicest class of finite extensions you have, and they behave well. And you can always, if it's not a Galois extension, you can always make it slightly bigger such that it is a Galois extension. So this is not a very strong hypothesis in what we do. Okay. So these Lie algebras, they are not really comparable. They live over a different field, they have a different dimension. But what we can do, I mean, at least for the fields, we can always extend this field again to the original field. So you could take the tensor product with E. So it just means this is, if you think about R and C, this is a real Lie algebra, and you extend the scalars to C again. So it's a bit weird. Somehow, first you forget it was a complex one, and then you reintroduce a complex one. But this is not just the Lie algebra N. Why not? Well, this has dimension this thing. So it's bigger than the original N. But what you can't show, and that's the main result maybe of the paper, that is if you do this Lie algebra is nothing else, well, it's isomorphic to, I used N, to all the conjugates of N over your Galois field, over your extension. So if this order is maximal, you usually write this as Galois of E over F, the Galois group. And so you take all the conjugate Lie algebras, you make a direct sum of it, then this one is equal to that one. And it makes sense because the dimension is the same. I mean, here you take this number of copies of that one, so they have the same dimensions, and they are really isomorphic. And the proof is, I will not give the full proof, although it's not that hard. But the isomorphism is really, you get it for free. I mean, showing it as an isomorphism is maybe a bit more work, but giving the isomorphism is really easy. Why? Well, you know, from n to n sigma, you always have this map phi sigma, the sigma linear isomorphism. That's how we defined n sigma. So there is always a natural map going from n to n sigma. And so what we do, our map psi, which goes from, well, I will just take it from nf to this direct sum. It is just mapping an element x to phi sigma of x, and this in all components. So you have a natural map from here to here, and you just glue them all together, you get one big map, and then you look at it over the field F. And that's all you do. And then what you can show for this map is if you have elements x1 till xk which are linearly independent, then their images will be also linearly independent.
So that's a digit sum of Lie algebras, of ideas.
I'm sorry?
It's a digit sum of Lie algebras.
Yes.
Ideas.
Yeah, they're all ideals. And so this is over F, and this is over E. So if you take the underlying and you go to the bigger field, it always splits. It's never indecomposable. It's always a direct sum of ideals. Okay, and this is really the main tool, because once you have this, I mean, you show immediately that this is an isomorphism. And in order to show this, you just use, I mean, if you have a linear combination here, you can use this property to see that the coefficients, they really satisfy, I mean, sigma of every coefficient is itself. And then you use the property that this is a Galois extension to conclude that the coefficients lie in your smaller field, and so that you have a linear combination here. But okay, I mean, I won't go really in the proof, but I just wanted to show you that this map is really the natural map you get. This is no very hard to construct map, it's the natural thing you can do. Okay. And why is this such an important result? Well, it allows you to show that under certain circumstances, you can recover your Lie algebra from its underlying Lie algebra. So a corollary, suppose that n is defined over F. So it means it has a basis with structure constants in F, or said differently, it means that, yeah, this is like an extension of a Lie algebra over F to the bigger field. Then NF isomorphic to MF implies that N and M are isomorphic. If, and you have two possibilities as conditions, so it's one of the two is sufficient. So either you have that N is indecomposable, or the second option is that M is defined over F. So if both of your Lie algebras are defined over the same field F, it's okay. Or if the first one is indecomposable, then you really get this.
So, sorry, what is the theorem saying in the case of real complex? It's just that
You mean the one?
that complexify a real algebra?
No, if you start with a complex, you take the underlying real, and you complexify it again, then it's a direct sum of two Lie algebras, namely the original one and the conjugate Lie algebra.
So you complexify
The underlying.
a real view, a complex viewed as real.
Yeah.
Okay.
So it's a bit weird. So you start with something complex, you forget it was complex, and then you make it complex again. It sounds like, why would you ever do that? It's like silly.
So you double the dimension.
Yeah, but you double the dimension, and then it also splits, really. But it's, I mean, the first time you read it, you have to read it like 2 or 3 times to realize what is going on. You forget the structure and you reimpose the structure again. But it gives you a very nice result. And so this is one of the consequences, that sometimes you can recover your Lie algebra. And the proof is, I will just prove it so you have at least one full proof. So if n is defined over f, this implies, and this is what I explained a bit earlier, this implies that all the conjugate Lie algebras are the same. So it means that n sigma is isomorphic to n. In other words, this direct sum I had of n sigmas, this is just n plus n plus n. You have k copies of n. Okay. And we know, I mean, you assume that this holds, nf is isomorphic to mf. So what is standing here is nf tensor with e. So this is equal to the same thing with m. I mean the same, it's always isomorphic, but I will just write it this way. And so if you do the same thing for m, I will rewrite it here. You have the same direct sum, but with conjugates of n. Okay. And so I have two assumptions. Well, I have either the first or either the second. Let's start with the first. If n is indecomposable, what I have here is a sum of indecomposables, and I also have a same sum here of the same length. So this implies that all these must be indecomposable as well, and that each one of these is isomorphic to one of those. And so the first one is just m. I mean, the identity is also in here. And so it implies that m is isomorphic to n by comparing the indecomposable components. I mean, you have two sums. This is indecomposable, means that it must appear somewhere over here. In the second case, m is defined over f, so it means you have k times the same Lie algebra here. So we have n plus is equal to the same sum of m's. And again, by comparing the indecomposable components, you can again show that m must be equal or isomorphic to n.
So, sorry, the decomposition of a Lie algebra in decomposable factors.
Yes.
Is unique?
I mean, up to isomorph, yeah, the components are not unique, but I mean, they are isomorphic, the components. Does that make sense?
Okay, up to isomorphism,
They are unique.
it's unique.
Yeah, but the decomposition is not unique. I mean, you could have several decompositions with, I mean, but if you reorder them, they do it, I mean, they are isomorphic. Yeah, yeah. So that's crucial for doing all these things. Okay, maybe. Okay, I don't have a lot to say anymore. That's good because time is up. We're almost up. There are still two things I want to say. The first is like the most general theorem. What can you conclude from the fact that underlying Lie algebras are isomorphic? So suppose that the underlying Lie algebras are isomorphic, and you write n as a direct sum of indecomposable components. Then the conclusion is that M is isomorphic to N1 to sigma 1 up to Nk to sigma k for some sigma I in the Galois group. So basically, the example or the construction I gave for constructing Lie algebras with the same underlying is the most general thing you can do, up to, of course, taking direct sum and taking different sigmas for the different direct, the different components. Okay, so that's, so for real and complex Lie algebras, what does it say? Suppose you have two complex Lie algebras, which are isomorphic over the reals. Then if you write one as a direct sum of indecomposables, then the other one has the same decomposition where sometimes you take complex conjugates. That's what it's saying. And so the question that I still have, which is open for me, so I said before that if a Lie algebra is defined, let's write it over R and C. So assume N is defined over R. So N is a complex Lie algebra. Then we know that the complex conjugate is isomorphic to the Lie algebra itself. But what about the other direction? I mean, I don't know a single example where the other direction is not true. So the only examples I know where the complex conjugate is equal to the Lie algebra itself, well, equal up to isomorphism, is when it's defined over R. And I don't believe this to be true, but it's just so hard to find counterexamples for this. And okay, maybe it is true, I don't know. If it would be true, it would be very nice, because this is a bit like saying if a real number is equal to its if lambda is equal to the complex conjugate, then lambda is real. This is like the Lie algebra version of this type of thing. It would be very cool if it would be true. I don't expect it to be true, but I mean, for me it's very open whether this holds. Or you could, of course, formulate it in general for field extensions.
So the meaning of defined over R is that it has a real form?
It has a real form, yes. So you can write it as some real Lie algebra, tensor C. So it has some basis with structure constants in the real numbers. And well, the hard thing in showing anything about this is that it's already hard to show that something has no real form. It's also very hard to show, I mean, the only techniques I know to show this are the same as I have to show that this is not true. So somehow the methods really coincide, and that's what makes it so hard to say anything about this. Okay, thank you.
So that 10-dimensional example you got is the smallest one? You know?
I don't know. No, I don't know. Ah, wait. You mean over all the Lie algebras? No, for sure not. Over two-step nilpotent, I don't know. If that's the smallest two-step nilpotent.
But is it the smallest known?
Ah, smallest known, yes. I mean, but I mean, if you look at the classification up to dimension 7, there are no examples there. But I don't know if there's maybe in 8 or 9 dimensions another example which does the trick. But for sure, if you look at all the algebras in dimension 4, there are also examples where it's not true, but then not two-step nilpotent, of course.
Any other questions? Okay, let's thank Jonas.